The point of chapter 3a is then he introduces you to a new vector space and says, this is what we're going to study. So nobody cares about vector spaces, but also this particular vector space is the one that we really care about.
So all the stuff in the midterm is actually
Yeah, so I'm not even going to include, like, there might be questions about dimension on the midterm, but not the sort of later stuff with the, like, anything covered in the homework basically is what I consider to be like acceptable stuff. So identifying that something is a basis, basic ideas of vector counting, the relationship between the number of linearly independent vectors and the dimension of a space. If you know that you've got the right number of vectors, you either have to check for linearly independent or you have to check for spanning set, right? Okay. Okay, so we're going to spend time talking about the midterm tomorrow.
Wait.
Is the midterm tomorrow?
No, Thursday.
Yeah, it's the midterm is Thursday. Right?
You scare me.
I was like, wait, is there a midterm? Is there not? I thought I scheduled a midterm. Like, you guys could have just tricked me right there and I would not have any idea. Really missed out on your opportunity. You shouldn't be intimidated by this one. I think it's gonna be pretty straightforward. So. Well, okay, it's okay to be intimidated by the class. Hopefully, I'm trying my best to make it less intimidating. Okay, so what I want to talk about today is the first thing I want to say is I'm gonna the last thing in 2C that we did yesterday, and I'm just gonna remind you because it was the end of the class. The very end of 2C was the theorem that said that if U1 and U2 are subspaces, this is a really useful theorem that's going to come up in the homework. I'm going to assign the proof to you to read because it's not a complicated proof at all. It's just a vector count, basically, right? If U1 and U2 are subspaces of a vector space V, then the dimension of U1 plus U2 is equal to the dimension of U1 plus the dimension of U2 minus the dimension of U1 intersect U2. You guys both invented this theorem for me last time and actually showed me basically the idea of like how it should work. Okay. It's basically you write a basis for this down and a basis for that down and you just count. Right. So the argument is long, but it's not hard. It's not a hard proof at all. So what I want to move on to is talking about like what Axler really cares about the most, which is linear maps. So Axler specifically says in the textbook, and I know that some people would read it because I heard people laugh when I said that, he actually says, no one gets excited about vector spaces. I don't know, I get excited about vector spaces, but I mean, it's really something like, oh, we spent chapter 2 talking about vector spaces. Nobody gets excited about vector spaces. The whole point of studying vector spaces is to get to the point where we can talk about linear maps. So we're going to add the additional assumption now that you're allowed, and I will tell the grader this, that you're allowed to let F be R or C, and V and also W can now be assumed to always be vector spaces. So there you go. You get W for free. Okay. So the object that we're going to study, so before I actually write this definition down, you have studied these objects at length in your earlier linear algebra classes. If you have ever performed a matrix multiplication by a vector, you have studied linear maps. But in 206, in linear algebra 1, the perspective on linear maps is basically, to a greater or lesser extent, the idea that all we really care about is matrix multiplications and functions defined by matrix multiplication. And what we're going to do is we're going to leave matrices off as long as we can and study these linear maps without referring to matrices, and then we'll sneak them in when we need to later. Okay. So from this perspective, linear algebra is not the study of matrices and vectors. It's the study of linear maps on vectors. Linear transformations maybe is the name you would have seen it in if you took Lay's book for 206. So a linear map is a function. He's going to use T. It takes inputs in V and outputs in a vector space W. So it has vector space inputs and vector space outputs, satisfying two properties. So the first thing we want is called additivity. So T of u plus v is equal to T of u plus T of v for all u and v in the vector space. T splits over its inputs. That's what it means to be an additive thing. And I'm going to point out here that it is usual notation when we're talking about linear transformations to treat them like multiplications. So T of u and T of v are often written like this. T of u plus v is Tu plus TV. And you're supposed to think the operator T, the linear map T applied to the vector u. Okay, so this is additivity. Yep. That line? No. I don't know why that was there. If I did that, I apologize. And two, a property called homogeneity, which means that if you have T and you apply it to some scalar times a vector u, so C is some scalar now, that scalars pull out. C times Tu for all C in your field, every scalar, and for all vectors in your vector space. Okay, now, amusingly, what this means is that lines aren't linear. Which is irritating, because lines aren't linear, but they're not. So we can actually see that lines don't set, that a general line in R2 doesn't satisfy these properties by imagining. So I could ask the question, is y is equal to mx plus b a linear function? And the answer is no. The reason it's no is because of this b, right? Y of x1 plus x2 is equal to m times x1 plus x2 plus b, which is mx1 plus mx2 plus b. If I add vectors in the input and I compute the output, this is what I get. But if I compute y of x1 plus y of x2, I get mx1 plus b plus mx2 plus b, which is m times x1 plus x2 plus 2b. And actually from there, you can actually tell me the only linear line. What condition needs to hold on y equals mx plus b in order for this to be a line? It should be linear in our setting right here. B has to be equal to 0 for a line to be linear. A line is linear. I just writing that down because it's so absurd, right? A line is linear only if f of 0 is equal to 0, which is going to force the b to be equal to 0. Okay, so lines have to pass through the origin is the question. A linear function is a function that maps the origin to itself.
I was just going to say in connection to the homework, is that why it's like lines that go through their origin are the only subspaces within like R2?
Yeah, so lines through the origin, we need that because the fact that 0 stays inside the subspace, basically we're trying to set up the definition of linear maps so that subspaces get sent to subspaces. If I have a map that takes 0 and sends it to some place that's not 0, I might not get a 0 in the image of the map. And if that means that the image of a linear map won't be a vector space. So what we're trying to build here, the big picture is we want operations that take in vector spaces and produce vector spaces. And that means 0 must be sent to 0, which we'll prove at the end of this. Okay, so let's make examples of linear maps and why these are studied so aggressively across so many different pieces of mathematics. So here's some really dumb ones. T is equal to 0. So the 0 operator is linear because by the 0 operator, what I mean is Tx is equal to 0 for every x in v. Well, that seems pretty obvious to me that if you took T of x plus y, which is 0, and T of x plus T of y, which is 0 plus 0, that those are equal to each other, right? So the 0 operator is sort of trivially a linear map. The other trivial example one is the identity map. I. What does I do? I takes an x and spits x back out again. That's linear. Those aren't very exciting examples of linear maps. So let's get one that is the heart of my own study in research mathematics, which is why linear algebra is the unifying language of all of mathematics. So the derivative operator, d of AF plus BG is equal to A d of F plus B d. So differentiation. Differentiation is taught in calculus because it's a linear operation, right? If I take the derivative of a polynomial, well, polynomial we already know now is a vector, right? We're thinking about polynomials as vectors. If this is a vector, this is a sum of two vectors. Well, we do this all the time. You're calculating a derivative, you're doing linear algebra without thinking about it, because you're taking the derivative operator, you're using the linearity to break the operator up across the inputs, and then computing these on this side, and you're always making the assumption that the thing that you got out of doing this split is equal to the thing that you started with. But the only reason that holds is because the differentiation is a linear operation. So they don't point this, I mean, they point it out, but they don't tell you that secretly it's all holds together because you're working with a vector space linear map, right? So differentiation is a linear map. And likewise, you do the same thing when you integrate. The integral of x squared plus 3x dx, everyone in here, whether you wrote it down or not, in their heads is doing this. Oh, it's the integral of x cubed dx plus 3 times the integral of x dx. But as soon as you do that, you've used linearity. You've broken it apart across the sum and you've pulled the scalars out. Integration is a linear map. So integration is a linear map. Yep.
I know this question sounds really dumb, but is there a way to visualize this?
To visualize a linear map? Okay, so what you're hitting right here, so that question right there is a beautiful question. And the reason it's beautiful is because what you're asking me to do is to tell you whether or not this class can be made concrete. And the answer is no. This is the beginning of the deep level of abstraction that happens in your algebra, and it's the specific reason why this class is so hard. We are characterizing a bunch of examples by way of nothing except a rule. So when you think of a linear map, what you should do is carry around examples in your head of the concrete examples of things that do it. But you can't visualize this because all it is a list of rules. There's no real way. There's no real way to visualize the fact that all we're doing is making two algebraic rules happen. So when I say a map is linear, I mean this, but there's no picture that I can use to draw that for you, right? If I could draw a picture, I would love to. The best I can do is give you a bunch of examples of things that act in a linear fashion. And so when you think, when a theorem comes up or a new idea comes up, you have to refer back to something like, okay, what would differentiation do, right? Another one that you guys have seen a bunch of is matrix multiplication. If I have this one may actually put this back in the land of like Math 206. Why do we spend so much time in 206 talking about matrices? Because any function that's defined by multiplication by a matrix is also linear. Because t of x plus y is equal to a times x plus y, which is ax plus ay, which is t of x, t of y. This is about the best I can do for making these things concrete. So give you lots of examples of concrete linear functions. But there's no big picture that I can draw about what's going on.
Is like a linear transformation the same as a linear map?
Linear transformations and linear maps are essentially the same words. It's different terms for the same object. Yeah. So basically, when I say linear, every time I use the word linear with reference to a function of any type, I mean it carries these two properties, whether it's a map or a transformation or actually we use the word operator later. All we mean is I can split it apart across sums and I can factor scalars out of it. Okay, now at some point I told you guys, I think, did I give you guys the von Neumann quote about like nobody ever understands this stuff, they just get used to it? Right. This is where this happens in here. Right here. Because everything is going to seem like it all of a sudden gets way more abstract than what we've been doing before. So I'm going to tell you that what we're going to get to is the idea that and this is why this is such a lift in abstraction, we're going to make the claim that the set of every linear transformation on a vector space is itself a vector space. So we got this second order vector space living over the top of vector spaces. And again, this is the hard part about this class is not getting around the idea that you understand these ideas in some sort of pictorial way, but that you've seen the ideas enough that you can use them without paying attention to the weirdness of what we're doing. They are just ideas that we're batting around with each other. They're ideas that have concrete examples like differentiation, integration, but we're studying that, we're sort of studying all of this at the same time at an abstract level. And this is why this class is so hard. Okay, is that we are getting away from the idea of studying concrete objects like in 206, where you study vectors in Rn and matrices that are n by n, right? We're trying to do it sort of at a high level all at once. And you can get a surprising amount of math out of the ideas that we're going to be talking about today. Okay, so before I go on, I know the weirdness of lines not being lines is, or lines not being linear is pretty irritating. There's even a whole category of things that satisfy, that look like lines that don't go through the origin, which is, they're called affine maps, if you've ever seen that term anywhere before. So an affine line is a line that goes through a point that is not zero, or that doesn't hit zero. All right. Make sure, this is one of those definitions that is central. So if I say T is a linear map, you should know instantly what I mean is split over sums and factor out scalars, okay? And it's helpful if you carry on idea, like examples of what they are as well. So what we're gonna do is we're gonna build some theorems about the way these things behave. And we're gonna go a little bit slower through this section because, again, the lift of abstraction here is a lot. So we're going to slow down. If you guys have questions about stuff, I want you to ask me, right? Mostly reading and doing these exercises is going to get you more familiar with how we do this stuff. So it's not hard, it's just weird. Okay, so suppose that V1 to Vn is a basis for V. And W1 to Wn. Notice these are the same n now, right? These spaces are of the same dimension. We've got a basis of size n here and another basis of size n here. W1 through Wn is a basis for W. Then there is a unique linear transformation T from W, sorry, from V to W with T of VI being equal to WI. So what I mean is, yep, it is necessary that these are the same dimension. So what I'm saying is if I've got a vector space with one basis and a different vector space with a basis of the same size, that I can map this basis onto this one. If there's too many vectors here, I can't do that. If there's not enough vectors, I can't do it. This is a precise one-to-one matchup. I'm going to make a function that eats V1 and spits out W1 and eats V2 and spits out W2 and all the way down the list, right? V3 goes in, W3 comes out. You guys have taken any sort of advanced algebra of any kind, essentially what we're, or if you've seen the word isomorphism before, eventually what we're going to show is that this is an isomorphism. So that basically these two vector spaces are the same, right? That's far in the future, but if you've seen an isomorphism, this is the first step towards that. Okay, so how would we prove that there's a unique function T that goes from V to W that does this? So if I want to show something is unique, first thing I have to do is show it exists. And then once I've got it, I'll show it as the only one that does what I want it to do, right? So this kind of uniqueness theorem, I'm going to show you what the transformation is, and then I'm going to prove it's the only one that does it. So first, we'll show that T exists. we're going to define P from V to W to be the function in a vector in V. And I spit out the same coefficients, but with the other basis. So I'm defining a function. So what this function does is it looks at a linear combination in the basis V, and it spits out that same linear combination, but in the basis W. That make sense? Okay. So I've got to show some things in order to show that T is linear, right? I've got 3 things to show. First, I have to show you that this condition holds, that T of Bi is equal to Wi, that the basis vectors make the basis vectors come out. And I've got to show you that it respects sums, so it's additive, and I have to show you that the scalars factor out. So I've defined this thing, but just by definition, it's not obvious that it's linear. It's a function. Why is it well defined as a function, actually? How do I know? So by well defined, I mean, how do I know that it only for each input, it only produces one output and not multiple outputs? Yep.
Is it because of the, like, the exponent of the size?
It's not the size of the vector spaces is the issue. There's something else. You're on the right track though. Yep.
The basis and vector and V or W is a unique combination.
It's the uniqueness of a basis, right? So if this is a basis for V, then every vector you write here you can get each input exactly one way in the basis. And since this is a basis, only one possible output can come from the input, right? So the uniqueness of representation in the basis is why this is a function at all. So this is a unique linear combination of the V's. There's only one vector that is these linear combinations of the W's. So the fact that we have a basis here is intrinsic to the fact that this map holds, right? That this map is a function.
Do you only really need the linear independence of the basis?
I mean, the spanning set means that it's defined on all. The spanning gives you the fact that all of V is the domain of P. If it wasn't a spanning set, you might not have all of V being the vectors that you could plug in. So you really do need both parts. So that is a question that is way, way deeper than we're going to deal with today. But that's actually what I mean when I say it's an isomorphism. It's that this actually does give you a bijection between the vector spaces. So yeah. I mean, if you guys remember where the idea of coordinates come from, or like if you've done coordinate vectors in your 206 classes, this is the map that ends up being the coordinate vector transformation from one vector space to another. Okay. This is an important map. Okay. Is T of Vi equal to Wi for all I? Is that true? Well, which particular collection of C's would you use to get W, say V1 to fall out? Well, 1 for C1 and 0 for all the rest of them, right? But if C1 is 1 and all the rest of the C's are 0, then the output is going to be W1. So V1 goes to W1 because if you let C1 be equal to 1 and everything else be 0, the 1 just carries over to the W1. So this holds because you could just let Ci be equal to 1 and Cj is equal to 0 for J not equal to I. And that will make that map have this behavior. Basis element in, corresponding basis element out. Why is this map linear? Well, suppose you took a combination of vectors on the input. What do you need to show? You need to show that computing T of the sum of vectors is the same as computing the sum of T applied to the vectors. I want to show that these two things are equal, and that would mean it was additive, right? So what I'm going to do is I'm going to compute this on this side. T of U plus V is the same as T of C1, yeah, C1 V1 up to, it's like working on a tight space here. This is T of C1 V1 up to Cn Vn. That's the representation of the vector U, plus D1 V1 up to Vn Vn. That's the representation of the vector V. Now I can't apply T to that yet because T is supposed to have a constant times V1 and a constant times V2 and so on. So I rearrange this into C1 plus D1 V1 up to Cn plus Dn Vn. And now T knows what to do because now you've got it's arranged correctly, right? Now T says, you've given me a linear combination of these. What should I do with it? Well, I should spit this out as C1 V1 times W1 because that's what I do. I look at the coefficients and I just swap the V's out for the W's. Remember now, the goal is to show that this is equal to, we want to show that this is equal to T of U plus T of V. Don't get lost when you're doing these arguments, right? So we're trying to compare these two structures. So we're actually pretty close to getting this form, which is break it back apart again. So I just multiplied out and resorted it. But this is T of U. This is T of W. Not a hard argument, but this shows that like this style of argument is very common when you're dealing with linear maps. You have an input, you compute what T does to the input, you do some sort of resorting and you show, oh, I could have also computed it this way. All right. Okay, a very similar argument shows that it does the same thing for scalars. So I'll leave that part and we'll say, similarly, E of CU is equal to C of TU. So what that means is if it's additive and it's homogeneous, then E is linear. Linear map. So now what? What did the theorem say? So this is what we've shown so far. We've shown T is linear. Okay, that's good. So T is a linear map. Check. T of Vi is equal to Wi. Check. T is unique. T is the unique function that does this. We have not shown yet. Right? We showed that T is a linear map by showing these two properties. So we've shown that Ti of Vi is equal to Wi by just choosing the right scalars. And the last thing we need to show is that T is the unique function that does this. So this is sort of a second introduction to proofs class. How do I show something is unique? Sure, suppose you got another one and show it must have been equal to the one we've already defined, right? So when you're showing something is unique, you posit another object and show it must have been equal to the original one. Okay.
Professor?
Yep.
Can you re-explain that the third line down?
Which one? This one here?
Yeah,
Or
like
this one?
I understand when you apply the T to the D1 to the
So you got this.
Yeah, because of that T of Vi, right?
Because this is what T does, right? Yeah, T just switches the V's for the W's.
W, okay.
So then I use the distributive property to get the vectors multiplied by it. So it's C1W1 plus D1W1 and C2W2 plus C2W2, just algebra. And then I took all the C's and collected them together
Okay.
and all the D's and collected those together. But what would T of U have been? T of U would have been T times C1 V1 plus Cn Vn. And what does T do to that? It turns it into C1 W1 up to Cn W1,
Oh,
which
so
is this,
why it's
that's this dude right here.
Okay.
So it's like I was working, the other common approach people take this is they work backwards, right? You start in one direction and compute this way, and you start in this direction and compute the other way, and you just hope you meet in the middle somewhere. Right, really common when people are proving that these maps are linear.
And then what are you saying up here? Like,
Where?
the TCU.
This is like
It's like
the scalar factors out, right? For C in the field. I should just do it.
So, okay, so
Let
that's
me,
not
let
first.
me just do it real quick, right? So the idea here is if you took TCU, that's the same as writing T of C times C1 V1 up to Cn Vn. But that's the same as T times CC1 V1 to CCN VN just by algebra, right? Distribute the C across everything. But then what does T do when it sees a linear combination of the V's? Gets rid of the V's and puts the W's in, right? Okay. So this is CC1 W1 up to CCN WN, but now every term has a C in it. You can just factor it out. But I know what vector T turned into this vector.
So to show this is a linear map, you have to show the additivity and the
Yes. Homogeneity. Yeah.
homogeneity. And then why did you say like TVI equals WI?
That's a bonus. This particular map is linear, but it's the special linear map that exactly changes the basis map. That was the definition of the function that we were dealing with. So I'm giving you the rule for the transformation. The same way if I tell you f is equal to x squared, I'm telling you not just that you have a function, but exactly what f does. I'm giving you a function rule that has a very specific behavior, right? So this is the specific function that takes a vector space in one basis and reproduces the same vectors in the other vector space. So it's almost like if you've seen change of basis before, this is basically a change of basis matrix, right? I mean, it's the high end linear map version of a change of basis matrix. Yep. Yes, that because U and V are elements of the vector space V, then each one of them can be expressed individually as a linear combination of the elements of V, right? If U is a vector in V and V is a vector in V, then in the, remember we said that V1 through Vn was a basis for the vector space V. So because they're in the vector space, that means that U is equal to C1 V1 plus Cn Vn for some constants C1 to Cn, and then V is equal to D1 V1 up to Dn Vn for D1 up to Dn in F. So we're saying if these are in the vector space, then we can express them in terms of the basis. So T of the sum of two vectors is the same as replacing those vectors with their unique expansions in terms of the basis. Then I resort things with algebra. Then T knows what to do because I've got the linear combination of just one V and one V2 and one V3 and so on. The expansion, the thing is that the way we defined T only works on the expanded vectors. Remember, we defined T to be the operator. So I have to do the expansion. I have to do the expansion because I made a definition where I said T is defined to be the operator that takes C1 V1 to Cn Vn and spits out C1 W1 to Cn Wn. That's the definition of T. T doesn't know what to do if I don't have an expanded vector.
So is that in like the theorem when you say T of V1 equals W1?
That's a consequence of the way we've defined the theorem. So the definition is this: a consequence. This is not part of the definition, a consequence of the definition. So we have defined the unique linear map that has the property that T of Vi is equal to. We did not define it. The fact that we've defined the map this way forces the T to have this behavior. So this was the assumption. This is a consequence. All right. All right. We keep wrestling with this stuff. I know. I did it myself. I've done it. I did it twice in finite dimensions and then again in infinite dimensions where it's even worse. So keep wrestling. And then I decided to become an infinite dimensional linear algebraist in some sense. So there must be something good here. Okay. So where were we at? What have we actually shown at this point? We've shown. Oh, good. You had a question. Oh, you're gonna tell me where I was. Okay. So what we have shown is, so I'm going to give you a heuristic, so just so we don't get lost. What we did was we defined T to be equal to the map that takes this. We made that definition, and what we've shown is that T is linear and that T of VI is equal to WI for all I. And what we need to show is that T is unique. So what we're going to do is I'm going to write down another linear map that has this behavior. So we're going to assume that we have a different map that does this, a different map that is linear and also has this behavior on the basis. And we're going to show that it must have been this to start with. I didn't even tell you what the output is. Okay, so I'm going to assume I've got something that has these two properties and show that the only one that has these two properties must have been the map that we started with. Yeah, keep yelling at me if you guys don't understand things that are going on here. Like I said, this is a major turn in the level of abstraction in here. Suppose S is linear and S of VI is equal to WI. Or I is equal to 1, 2, da, 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 da. So we're going to suppose we got another one. We're going to show that it must have been T to start with. Okay, now let C1 up to Cn be given. And T goes first. So let's see what is Cn be given. Then I'm going to make this argument. T Cj Vj is equal to Cj T of Vj. Why is that true? C is a constant, or sorry, not T. Sorry, this is supposed to be S. S of Cj Vj is Cj S Vj. Why is that true? S is linear, and so S is homogeneous, right? The fact that S is linear means this must hold, right? S is linear. We assumed S was linear, so it must do this by homogeneity. Also, that means that S of C1 V1 plus C2 V2 up to Cn Vn must be equal to C1 S of V1 plus S of V2 C2 S of V2 Cn S of Vn. Why is that true? Additivity, right? S is linear. I got a bunch of sums. I can break it up, and then this fact lets me pull all the C's out, right? Okay, now, what is this equal to? Same vector. What does T do to it? This spits out this, right? Okay. So this representation is unique. This input is the same for both functions. So the fact that we have unique representations in both the and also we have one more line to make here. What does S do to V1? By assumption, what does S do to V1? Turns it into W1, right? So if I just, then that means this must be C1 W1 up to Cn Wn. Is it even possible for S to be a different function than T? No, because this is a unique representation. So the input of S and the output of S are the same as the unique inputs and outputs of T. So notice we didn't define S anywhere. We just said the properties that S has. But just from those properties, we've recovered the same exact input-output relationship that T has. So S must have been defined by the same rule as T. Does that make sense? The inputs were unique. The outputs are unique because of expansion of basis. The action of S is the same action that T has. So could S be a different function? And the answer is, if it's a function that has the same input and the same output, it's the same function. Yep. Yes, because it's possible if these weren't linearly independent. So if you think back to earlier linear algebra classes, if you have multiple representations of a vector, you can define functions that actually specify a unique representation. And you might get the function with like a kernel in it, for example, right? The input vector could have something that gets sent to 0 and a piece that reproduces the output, and you get the same, you get the same outputs, you get different outputs from the same input, I guess. guess is what I'm saying, or the same outputs from different inputs. It doesn't violate the definition of a function. So it's if the same, what we've shown here about t is that it's got this unique correspondence between input and output, right? If it was the case that there was not a unique correspondence, you could have a function that was 1-to-1 between some domain and some output, and a function that was 2-to-1, for example. So the rules could be different. The idea is the rule that defines S could be different than the rule that defines T. The basis, I mean, it's because of this bijection that you're talking about, right? The fact that we've got a basis here makes that impossible. Yep.
When you say the rule that we define as or t, what do you mean?
So what I mean here is S is a function that if I feed it this vector, which is a unique vector in V,
Yeah.
I get this vector out, which is a unique vector in W, right?
Yes.
T takes the same unique vector in and puts the same unique vector out for every single input. Every input of S agrees with every input of T, right? Any vector you feed S does exactly the same thing that T does to it. So if two functions have the same behavior on every single input, they are the same function,
Okay.
right? T must be equal to S because every input vector, if I think of S of V, is equal to T of V for all V in the vector space. Every single V that you feed in, S and T do the same thing. So if the inputs map to the unique outputs precisely in the same way for every input, they must have been the same function. Yep. That's, yeah, so the idea is I'm saying any other map that has these two properties must have had the same rule that we use to define T. Yeah, I don't define S here, right? The fact is what we've done is we've recovered the definition of T from these properties, right? We're saying that these properties characterize the map. There's one map that is both linear and sends the basis elements to the basis elements. And we already wrote down the rule for it. Okay, so logically what we're doing is we're working in the converse. Yep.
So that line where S of Vi equals to Wi, it's just a property.
It's a property.
Whereas
So
what-
yeah, because what we already showed, I mean, so what we've shown already, if T is defined this way, then T is linear and T has this property. What have we just shown? If S has these two properties, then S was equal to T. So we've actually sort of got it's a biconditional theorem,
Okay.
right? It's an if and only. If T has this definition, then T has these properties. If S has the properties, then S must have this function definition. So that's what it means to be unique, is to have this like if and only if type setup. Is that okay? Weird. Okay. Okay, so maybe we should before I start working on the weirdness of the fact that these are vector spaces. Let's do something cute. You guys can tell me how this works. So here's a cute thing. Instead of a thing we're gonna beat our heads on it, let's do something cute. Okay, here's a very easy theorem. It doesn't even really deserve the name theorem. We're gonna say anyway. Theorem. If T is linear, then T of 0 is equal to 0. Now the statement is like, it's kind of lame, but the proof is cute. Proof. Does anybody who has not read ahead of the book, or is not going to quickly flip through the book, see any way we can do this? I give you, yep. Oh, we could work by contradiction, but oh no, there's a way cuter way than that. That'll work. What is that equal to? T, okay, on the one hand, this is T of U, right? Because U plus 0 is equal to U. So T of U plus 0 is T of U. But by linearity, what is T of U plus 0 equal to? T of U plus T of 0. So T of U is equal to T of U plus T of 0. So what is T of 0 equal to? 0. Subtract t of u from both sides. Why is this cute? Because it takes no work at all. What a beautiful little theorem that is. Every linear map must, I mean, we talked about this earlier, right? Linear maps must send 0 to 0. So they're set up, you shouldn't think of this as an accident. This is set up on purpose to make sure that linear maps take vector spaces to vector spaces. Right, so basically this theorem about the behavior on a basis, I mean, this is in the dimension n case, but we're gonna be able to show that a linear map coupled with this notion that because of the way we define linearity, it requires this function to send 0 to 0, that the range of a linear map is going to be a vector space. Okay, so that's kind of where we're going with this is linear maps map vector spaces and produce vector spaces. So they're compatible with the mathematics of vector spaces is the idea of why we're doing this. Okay, so I've got one, I'm gonna at least, okay, just so that you get a chance to, you know, when you're having nightmares about math tonight, laying in bed, thinking about all the awesome things you learned, well, not nightmares, beautiful dreams about abstraction in your linear algebra class. They give you some notation that you can use to like compile your dreams. So the set of all linear maps from B to W is denoted. So here you can start using fancy letters. L of V W. So when I talk about LVW, I mean the set of every possible linear map. It's like a family of functions, right? A set of functions. It's all the functions that are linear and have V as the domain and produce outputs in W. What do I need to show something's a vector space? That's a set. How does a set turn into a vector space? What do you need to have to turn a set into a vector space? If you remember way back 4 weeks ago, what else do we need? We need some properties, but it's even before we had the properties, we needed something for the properties to be built out of, right? What property, what we need things to, we just structure this somehow. So vector space wasn't just a set of things. There were some things that came along with those things. Addition, scalar multiplication. Would it surprise you to learn that S plus T is an addition on L of VW? I can add two linear maps together and get another linear map back again, right? If I have a linear map and I add it to another linear map, it stays a linear map. S plus T of X is equal to S of X. Yeah, that's there. I have defined an addition. What else do we need to make a vector space? Scalar multiplication. CS is a scalar multiplication. L of W, where you let CS of X be equal to C times S of X. And now we get the utterly bizarre and hyper abstract fact that equipped with those two operations, this amorphous blob of linear maps is itself a vector space. Axel doesn't even bother to prove it, he leaves it to you. Claim L of VW is a vector space. Oh, what a good question, actually. So it turns out, okay, so it's a vector space, doesn't have a basis. Well, one of the fundamental facts of higher mathematics is that every vector space has a basis. So yes, does it have a finite basis? I don't know. So I'll give you an example of what one of these might look like, right? So it turns out to be the case that you can think of if you let V and W both be equal to, say, R3. Let's make it even easier, R2. So two-dimensional vectors. Here's a vector space you guys have studied before. Wave in 206, at some point, you proved that every linear map on a vector space, every linear map on R2 could be represented as a matrix multiplication. You will learn that at some point. A linear transformation on R2 can be represented with multiplication by a matrix, which means every element of LR2 to R2 is A, B, C, D. You think about T of X is equal to this matrix times the vector X. So if everything in here can be thought of as a 2x2 matrix, does that space have a basis? Yeah. Because if you tell me what A is and what B is and what C is and what D is, you've told me what the function is, right? So this is actually, in this case, it's 4-dimensional. Yep. Okay. Well, I don't want to get it. So I don't want to get into that yet. Like I'm just giving you an example of what a family of linear maps might look like, right? So a specific case of a family of linear maps, when the vector spaces are both R2, are all the matrix multiplications by 2x2 matrices. And so these functions are precisely those functions that are represented by these matrix transformations, and we can think about them as having a basis. Okay. I mean, again, this is where that gets weird. So read the book slowly. Don't rip through it and like, oh, I read the book because you read it in 5 minutes and you recognize all the words, right? Next time we do new stuff, what we're going to talk about is how we take this idea of the vector space here and start using it to study. Well, this vector space comes with additional structure, which makes it different. All right, I'll see you guys tomorrow.